So I'm Louis, working at Holonym, and today my talk will be about our human keys. So our human keys consist of deriving cryptographic keys from human data. Okay, so what we are doing actually is having a decentralized threshold network using its private key to perform an oblivious pseudo-random function on the data committed by a user. Okay, so this human data could be biometrics or not. I mean, actually, it could be, as this famous saying, could be what you are, what you have, or what you know. And with the particularity that this data will be, most of the time, will be with really low entropy. Okay, as for example, with a social security number. So this user will commit and choose its human data, and from that data he will compute and it will map it to an elliptic curve, and then it will mask it to for some privacy reason, and then send this this elliptic curve point to the distributed threshold network of us, which name is MPC network. So just a few slides on this network, our MPC network. So here's the architecture of it. So we have different kind of nodes. We have proven nodes that will perform the computation. We have the bootstrap nodes that will like communicate with the proven nodes, and finally the relay node, which connect everything together to form the network and give the instructions to the whole network. So as an initialization of that network, we have this relay node that from the list of all the available nodes will choose the n value, which is the number of nodes composing a quorum. And from that quorum and that number n, it will choose and derive the threshold value. So quorum will be like this group of nodes sharing the same secret during one specific epoch. And so our network is also threshold, as it has been discussed earlier. So meaning that with a T out of n network, we have n nodes sharing the same secret, and T nodes are sufficient to recreate that secret. So in our case, we choose T to be around a third of n, but as Jonathan discussed earlier, I mean, depend on the trade-off between availability and security. So this T value could vary. So then, when this n quorum is formed, so when the n value are chosen, the relay node will have to pick the nodes to compose that quorum. So what our node selection here will be based on randomness. So the relay node will pick some random using DRAN. So maybe we could switch to InstaRAN instead, which looks quite promising. So from that random value, the relay node will sort the list of all the nodes, all the registered nodes, and then it will perform some liveness check on each of that nodes to actually to end up with a list of n nodes. And this is our approach, because such way, by using this DRAN API function, that makes any nodes can actually recreate this node selection by querying the same random value and verify that, especially in the case where a node has not been chosen, you can verify that the selection process has not been cheating on it. Yeah, for sure. Two different. Actually, in our case, we use only one relay node. So just like pinging every proven nodes to just like to verify that they are active and they are like willing to participate. Yeah, yeah, but actually each proven node can actually do the two first steps, right? And so at the end, if he can check that his range in the order list, I mean, like that the last picked a proven node was not like after each range, right? So a few words about the DKG. So here, for example, we have a quorum of 3 nodes. And so I won't go into details on that DKG, but just so these 3 nodes are like computing together the secret shares. It's based on secret sharing. So the secret is never combined because, as Jonathan explained also, we don't want any one point of failure. So it's actually happening with all the nodes generating their own secret and then having some secret sharing between all of them from all of their secrets. And we'll have also some identification for a board or for like bad intermediate results. And also we have a resharing protocols, which is quite similar to that DKG. So now back to our use case with this OPRF. So the user is sending his value, his point to our machine network, and the relay node will send over that point to the node. So in this case, we have a 2 out of 3, let's say. And so it is sufficient for the relay node to only ask 2 nodes of the 3 to perform the scalar multiplication. So in our case, the selection here about these 2 nodes among the 3 will be deterministic and with a uniform distribution, which could be easier for us like later, especially for the rewards. And then the proven nodes are doing the computation. So it's like 2 steps. First is the scalar multiplication between the private share and the user point. And they will also provide and generate a delay proof of that multiplication, proving that this scalar multiplication have been done with their private share and the correct private shares. And this is happening because during the DKG, each node has to commit his public share. And that way, later, the partial product could be verified. So then we have this verification phase using the eigenlayer AVS. So the relay node will transmit all the partial products and the respective delay proof to this AVS. And all the node will have to verify the proof based on the products. And from that, we could then reward and slash the proven nodes. And finally, after getting a consensus on the AVS, the final product is recreated by some just really basic Lagrange interpolation between all the partial products. And at the end, the final product will be sent back to the user, unmasked, and just like mapped back to a scholar. So that's it. That's how our OPRF for human keys is working. Thank you.
We have some time for a few questions, but otherwise our tea break is already started. So you can ask your questions. If you don't have any, you can take it for the tea break. Any questions?
If one of the provers, so actually it's a threshold. So yeah, if you pick like a sufficient low t value, then it's acceptable.
Okay, give it up for Louis, Tajan. Yeah. Thank you.